All right, welcome, ladies and gentlemen. We are going to finish off our calculus class with one last lesson. This is L'Hopital's Rule, how to find limits of things we called indeterminate forms. Let's go ahead and look at what this is going to mean. The first and probably the most, well, there's two most common ones. This is the first one we're going to look at. This is 0 divided by 0. In math, 0 divided by 0 is a meaningless statement. It has no value. It has nothing that we can do with this thing. But when we get into limits, well, in limits, sometimes this happens when we do a substitution. So if we have functions f of x and g of x, and if they're both 0 at x equals a, then the limit as x approaches a of f of x over g of x cannot be found, because when we do direct substitution, we get f of a is equal to 0 and g of a is equal to 0. And so we get this indeterminate form of 0 over 0. Well, there's a very handy little thing that we can do, and that's actually going to be L'Hopital's rule. This is when algebraic methods are complex, so we use L'Hopital's rule. In this case, well, let's just get into L'Hopital's rule before I get into too much overthinking things. So here's what L'Hopital's rule is. Suppose that if we got f of a and g of a is equal to 0 in our limit, or in our functions whatsoever, then and f prime of a and g prime of a exist, and that g prime of a is not 0, then we get this very nice statement that I have to put in the as x approaches a and as x approaches a. This is our L'Hopital's rule. So notice what this is saying. It says the limit of f of x over g of x as x approaches a is equal to the limit of the derivative of f divided by the derivative of g as x approaches a. This is for our indeterminate forms if we get this 0 and g of x is also 0. So when f of x is 0 and g of x is 0 at x equals a, we get to do the derivative. And what happens is, as we continue to do this, you might even end up, sorry about that, you might end up with you need another derivative or another derivative, but eventually you will get a value for the limit, a very easy value for the limit. So here's what you're going to do in solving these problems. You're going to substitute x equals a into your limit problem. If the result is 0 divided by 0 or infinity divided by infinity, we'll get to that in a moment, you take the derivatives of the numerator and the denominator. You then substitute a into that new ratio, and that will hopefully get you an answer. But like I said, if it doesn't, if you get another 0 divided by 0 or an infinity divided by infinity, you repeat that process until the limit is revealed to you. Now, there are 4 different indeterminate forms. Here are the first two listed here, 0 divided by 0 and infinity divided by infinity. Well, there are more indeterminate forms, but the ones that we cover in this class are the 4 here. These are the 3. If you want to include somewhere over here 0 divided by 0, that's fine. But in these 3 cases, these are the kind of weird ones. We get infinity divided by infinity, again, meaningless. Infinity times 0, kind of meaningless. And infinity minus infinity, very meaningless. Okay? And actually, even infinity times 0, that's a meaningless statement because infinity is not a number. If you have the infinity divided by infinity, you just get to use L'Hopital's rule as I mentioned before. However, the next 2 are a little bit more complex. If you have infinity times 0, you have to do a little bit of algebra or a little bit of trickery. Sometimes it's trickery, sometimes it's just a little bit of algebra, in order to manipulate the equation to make it look like infinity divided by infinity or 0 divided by 0. And once you have either of these, you can straight use L'Hopital's rule. You can scratch part 1. That was unnecessary. And likewise goes with the infinity minus infinity. If you get that, you need to also use a little bit of algebra to make it into a ratio. So we're looking for finding fractions. And usually this is going to be like a fraction minus another fraction, something like this. And what we need to do is we need to combine these two fractions with a little bit of algebra to make it a ratio, so then we can get these indeterminate forms, so then we can find the derivatives. All right, so in order to use L'Hopital's rule, you need f of x over g of x. So let's look at some examples. In example 1 here, it looks kind of ugly, but it's really not too bad. We're saying let's find the limit as x approaches 0 of this big function. And this is an f of x over g of x. So we already have a ratio, so we don't have to think about that too much. But the first thing you do when you come to a limit, any limit, first thing you do is you substitute in the value just to see if it's going to work. Well, when I substitute the value, I get the square root of 1 minus 0 all over 0 squared. And that becomes 0 over 0. Well, when it becomes 0 over 0, that means I can take the limit as x approaches 0 of the derivatives of top and bottom. Well, the derivative of the bottom is pretty easy. The derivative of the top is that square root is 1/2 times 1 plus x to the negative 1/2. Well, the derivative of negative 1 is 0, and the derivative of negative x over 2 is negative 1/2. Well, then I look at this again. Can I do direct substitution? Well, direct substitution is going to say this is 1/2 times 1 to the negative 1/2 minus 1/2. Ah, dang, that's going to be 0 again, and it's going to be 0 again down here. All right, well, that means let's find the derivative again. So because I have the indeterminate form 0 over 0, I can do that. It's okay to do that. The derivative of this, I bring down the negative 1/2. This becomes negative 1/4 times 1 plus x to the negative 3/2. The derivative of negative 1/2 is 0. 0. And the derivative of 2x is 2. Then I do direct substitution. And if I do direct substitution, I get negative 1/4. I get negative 1/4 times 1 to the negative 3/2 all over 2. Well, that's nice. 1 to the negative 3/2 is just 1. So now I don't get an indeterminate form. I get 1/4 over 2, which is equal to the negative 1/8. So the limit of this big ugly ratio is just negative 1/8. It's a very nice answer. You can verify this graphically if you want to. You can type in this function into your calculator, and you can say as x approaches 0, what's happening to my y values? And that would be negative 1/8. They'd be all approaching that value. All right, let's see about another one. There's a limit as x approaches pi halves of the secant x divided by 1 plus tangent x. So what we're going to do here is we're going to say, okay, well, let's think about plugging in pi halves. Well, if I plug in pi halves, I get some bad stuff happening. Secant of pi halves is undefined. And secant or tangent of pi halves is also undefined. So what we need to do is we need to look at one direction. So we need to look at, well, what's happening to this as we approach from the left-hand side or the right-hand side. But if we think about this going from the left-hand side and we plugged in pi halves, we got closer and closer to pi halves, this numerator is going to be going to infinity. And you can see that graphically for secant. Secant looks like this. If I can draw this correctly here really quickly. This right here is pi halves. And we know from the left-hand side, it's infinity. It's going towards infinity from the left-hand side. And 1 plus tangent x looks like this. That's pi halves. And from the left-hand side, it's also going to infinity. So it's kind of going into infinity plus 1. So here we get infinity over infinity. Well, since we have infinity over infinity, we can use the L'Hopital's rule. I get the limit as x approaches pi halves, and we're talking about from the left, by the way, because my answer would be the same either side. Oops, I don't know where the 2 came from. From the left, that's a minus sign. Okay, derivative of secant is secant x, tangent x. The derivative of 1 plus tangent is secant squared x, and you're saying to yourself, that doesn't look any more simple. And if I plug in pi halves, I still get all of those undefined values. You're right. However, you're wrong at the same time. This pi halves to the left, from the left, secant over secant squared cancels. Something over secant is like having a cosine times the tangent, which is sine over cosine, which means those cancel. So ultimately, I'm looking at the limit as x approaches pi halves from the left of sine x. Well, now I can plug in pi halves, and the sine of pi halves is equal to 1. Look at that. That nice big ugly limit is just equal to 1. That function approaches 1 as x goes towards pi halves. And what you could do for yourself, if you'd like to, is if you think about going from the right-hand side, well, on the right-hand side, I'd be going to negative infinity and to negative infinity, and it ends up being the same answer coming in from the left-hand side or the right-hand side for this particular problem. All right, let's look. I just have examples left over here, so let's go ahead and just keep moving forward, looking at x approaching infinity for a function here. Now, some of this you might have to really think about. The natural log of x, I always think about things graphically. What's happening as x goes to infinity? Well, natural log of x looks like this. As x gets really big, y just keeps getting bigger and bigger. So that means my numerator is infinity. And 2 radical x looks like this. And as x gets bigger, again, y continues to get bigger. So we get the indeterminate form infinity over infinity, which means we need to find the derivative. Using L'Hopital's rule, we say this is limit as x approaches infinity of, okay, derivative of natural log is 1 over x. The derivative of 2 radical x is 1 over radical x. And we can do a few things here. We can write this, we can flip and multiply. This becomes radical x over x. And if you want to get tricky, you can look at this. And if you remember that 1 over radical 2 really is root 2 over 2. Same thing, 1 over radical x is the same thing as radical x over x. So you can kind of think about it that way if you want to, or you can do the derivative one more time because this would still be infinity over infinity. So you can do the derivative one more time, or you can just think about, okay, well, this really becomes the limit as x approaches infinity of 1 over radical x. And that's actually what you would get if you took the derivative of this fraction one more time, or the derivative of the top, derivative of the bottom. That's actually what you would get. Well, as x goes to infinity, I think we can do this one now. As the radical function goes to infinity, that becomes infinity. So I get something like 1 over infinity, but that, as x gets really, really big, my fraction gets really, really small, and it tends toward 0. And that's our answer. The limit of this function is equal to 0. All right, I have 2 more examples here. This one's a little bit tricky. If we were to look at this function, this, as x goes to infinity, that means this becomes infinity. And the sine of 1 over x, so as x gets really, really big, this gets closer to 0, and the sine of 0 is 0. So then we get that infinity times 0 piece. So here's how this gets a little tricky. And you may or may not see this on an A/B test for the AP Calculus. However, it's kind of a good thing to know how to do. What I can do is I can do a little bit of substitution. If I said u is equal to 1 over x, that means x is equal to 1 over u. And as x goes to infinity, u goes towards 0. So I can change this limit to look a little bit different. Now, like I said, it's going to be a little bit tricky here. So x becomes 1 over u times the sine of u. But now our variable is u, so we're talking about the limit as u approaches 0, because originally x goes to infinity, so u goes towards 0. Now, that doesn't, again, it doesn't look a lot easier. However, if I was to write this in a little bit different fashion, because 1 over u times sine of u is the sine of u over u, and we know this back from way back in the beginning of the year, the limit as the value of the thing goes towards 0, or the function, the variable goes to 0 of sine u over u is equal to a very nice 1. And that, again, that's the answer for that particular problem. We got the derivative. We could have done derivative. We could have done the derivative of sine u over the derivative of u and got that it was cosine of 0, and cosine of 0 is 1. Or you can just remember that little identity that we used way back when. All right, last one. This is going to be, oh, look at that. It's got to be the something minus something, the infinity minus infinity. As x goes to 1, as x gets closer to 1, this thing, the natural log of x, gets closer to 0. That means the 1 over this thing is getting closer and closer to infinity. Likewise, as x goes to 1, this thing is getting closer and closer to 0, so that means the fraction is getting closer and closer to infinity. So when we have infinity minus infinity, we need to combine those fractions. So here I need to multiply by x minus 1 over x minus 1. Here, natural log of x, natural log of x. So I get the value now of x minus 1 minus the natural log of x all over natural log of x times x minus 1. All right, now we have a fraction. Now we can see what happens with L'Hopital's rule. So x going towards 1. So let's do a direct substitution. We get 1 minus 1, which is 0, minus the natural log of 1, which is 0. Okay, natural, that means the numerator is 0. Natural log of 1 is 0. And 1 minus 1 is 0. That means, yay, we get the 0 over 0 form. So we can use L'Hopital's rule. Limit as x approaches 1 of the derivative of the numerator will be 1. Okay, the minus 1 goes to 0. The minus natural log goes to minus 1 over x. All over. Oh, man, it's a product. That means I have to do product rule. The derivative of x minus 1 is 1. So I get natural log of x plus the derivative of natural log of x is 1 over x times x minus 1. Okay, so again, depends on where you want to go here. If you want to do a little bit of algebra, this numerator becomes x minus 1 over x, finding common denominators, which means I can put this x into the denominator, and I can explain that to you in class if you so choose. But what I'm going to do is I'm going to get this. I'm going to say, okay, limit as x approaches 1 of x minus 1 over, okay, what's that going to be? The x has to go to everything here, so it becomes x natural log of x plus x minus 1. All right, now that might not have been a very clear step to you, but you could have plugged in, back up here, you could have plugged in a 1 and realized that you had to do the L'Hopital's rule again. Well, notice what we have to do here. If I plug in a 1, I get 0, and if I plug in a 1 down here, I also get 0, which means I need to find the derivative again. So the derivative here is going to be 1 over x times the natural log of x. Man, okay, so natural log of x times 1 plus x natural log of x, x times the derivative of natural log of x is going to be 1 plus 1 again, the derivative of that x minus 1. Oops, forgot my limit. Don't do that. Don't forget limits. Always write those. Okay, so, oh look, I don't get 0 over 0 anymore. If I substitute, I get 1 over 0 plus 1 plus 1. That's a nice number of 1 over 2, and that is my nice limit using L'Hopital's rule of the original function. All right, that is the end of this video. I will put an assignment for our textbook in the description below. All right, I will see you guys tomorrow. Have a great day.